This video is for class 9 physics, and right now we are doing the topic mass and weight from the chapter laws of motion under the topic gravitation. Okay, mass. We've been doing this mass since class 6. By this time you should be able to define mass. So mass of a body is the quantity of matter it contains. So the mass is a scalar quantity which I have studied in the first chapter. Its SI unit is kilogram, which is kg. It is a constant for a given body at rest and does not change by changing the place of the body. It is an intrinsic property of the body, internal property of the body. Internal property, okay. So it is measured by a physical balance or beam balance because the value of g, which is acceleration due to gravity, is same on both the bands. The mass of a body increases with its velocity, but this change is perceptible only when the velocity of the body v becomes more than 10 to the power 6 meter per second. This thing also has been discussed in the linear momentum. So now that is reaches close to the speed of light. So for a body moving with the velocity less than 10 to the power 6 meter per second, its mass is taken to be constant. The next thing is weight. The weight of a body is the force with which the earth attracts it. In other words, weight of the body is the force of gravity on it. So these two definitions of mass and weight suggest that they are two different things. The weight is a vector quantity, its direction is downwards towards the center of the earth. Unit of weight. Since it is force, so weight is measured with the unit of force, which is Newton. And the CGS unit is dyne. As you all know, 1 Newton is 10 to the power 5 dyne. Now, the relationship between weight and mass, that is formula of force. The weight of a body is related to its mass as follows. Weight equals to mass into acceleration due to gravity, where W equals to m into g, hence we shall get W equals to mg, which is the other form of F equals to ma, right? Because weight is force. Note, from equation 3.20, the SI unit of acceleration due to gravity, g, can also be written as Newton per kilogram. Remember, this is also the unit of acceleration due to gravity in place of meter per second square. This was also explained in the previous video on numerical problems. Since the value of g varies from place to place, the weight of a given body also varies from place to place. The gravitational unit of weight in MKS system is kilogram force, and in the CGS system it is gram force. 1 kgf equals to 9.8 Newton. We shall see this after some time in this video only. So, and 1 gf equals to 980 dyne. Obviously, a body of mass mkg will weigh mkgf. So it's very simple. If you are 40 kg girl, then your weight is 40 kg f, not 40 kg. 40 kg is your mass. The weight of a body can be measured by a spring balance directly in Newton and also by a physical balance in kgf. Comparison of mass and weight. Mass, number 1, it is measured of the quantity of matter contained in the body at rest. It is the force with which the earth attracts the body. So they are two different things. Number 2, mass is a scalar quantity whereas weight is a vector quantity. Number 3, its SI unit is kilogram, its SI unit is Newton. Number 4, it is measured by physical or beam balance. It is measured by spring balance, which is calibrated to read in Newton. Number 5, it is constant for a body and does not change with place, right? It is not constant for a body but varies from place to place because the value of acceleration due to gravity changes from place to place. This was also discussed while studying simple pendulum in the first chapter. So now we are coming to the last topic of the chapter, which is gravitational units of force. In MK system, the gravitational unit of force is kilogram force, kgf, and where 1 kilogram force is the force due to gravity or on a mass of 1 kg. Suppose you hold a mass of 1 kg on your hand, then you are feeling a force of 1 kg F. That is 1 kgf equals to force due to gravity on a mass of 1 kg. That equals to mass of 1 kg into acceleration due to gravity. Suppose acceleration due to gravity for a place is g meter per second square. Hence we shall get g Newton. So 1 kgf equals to g Newton, where g is the value of acceleration due to gravity of a place. Suppose the acceleration due to gravity of a place is 100, then 1 kgf will be equal to 100 Newton. Suppose in a place the acceleration due to gravity is 10, then 1 kgf will be equals to 10 Newton. On the surface of the earth, the approximate value of g is 10, therefore 1 kgf equals to 10 Newton for the surface of the earth. Since average value of g is 9.8 meter per second square, therefore 1 kgf equals to 9.8 Newton. For simplicity, we can take 10 Newton also. In CGS system, the gravitational unit of force is gram force. 1 gram force is the force due to gravity on a mass of 1 gram. That means if you are holding a mass of 1 gram on your palm, then you will feel a force of 1 gram force. That is 1 gram force equals to force due to gravity on a mass of 1 gram. That equals to mass 1 gram multiplied by acceleration due to gravity. Suppose it is g centimeter per second square. Then 1 gram force will be equals to g dyne. Again, g is the value for the acceleration due to gravity of a place. It can be 10, 100, 1000 depending upon the place. Here place means from planet to planet. Since the average value of g is 980 centimeter per second square, therefore 1 gram force will be equals to 980 dyne. So further 1 kgf equals to 1000 gf. So the relationship between the gravitational SI unit of force and the gravitational CGS unit of force is 1 kgf equal to 1000 gf. To an approximation, 1 kgf is assumed to be nearly equal to 10 Newton, which I have discussed. Then 1 Newton equals to 0.1 kgf or 100 gf. Thus, one can feel a force of 1 Newton by holding a mass of 100 gram on his or her palm as shown in the figure. Obviously, if we say that 1 kgf equals to 9.8 Newton, we mean that we have to exert a force of 9.8 Newton to hold a mass of 1 kg on our palm. That means we are exerting a force of 9.8 Newton if we have to hold a mass of how much? 1 kg, right? If we have to hold a mass of 1 kg, right? So this much for this video. Thank you so much.